So what people do is that they build a supercomputer model of the city and then simulate how sound propagates through the environment. So I'm going to show you one such simulation here. Can we have the light off or not? The lights on. Okay, it's okay.
These lights, turn all lights off.
Okay, thank you. Okay, so so there's a license. There's a what? But that's not full screen.
No, I think you won't do it for full screen.
Oh, here we go. Okay. Right. So if there's a light source, there's a sound source in the middle, and this is a simulation, a supercomputer simulation that shows you how the sound source is propagating through the environment. So you can see sound waves going across, right? And you can see sound reflected from the buildings, and some go through the building and so on. So this is a 1.2 second simulation of this sound source. And so there is a computer model that does it. And then, okay, let me show you this here. Okay, so this is a detail of. How come it doesn't show? Oh, I did wait a little bit.
Yeah.
I see.
Yes, yeah, adjusting adjusting the screen.
Oh, okay. All right. So now, so the simulation that I will show you is very expensive to calculate, to compute. So how expensive is it? So a 1.6 second 3D simulation that I just showed you in the city environment, about 3/4 of a kilometer, this dimension, takes 11.5 hours on a supercomputer with 256 CPU. Okay, so very expensive calculation. 12 hours on a Cray supercomputer. So what we do is that in many applications, we need to execute this code many times using different source signals. And if each calculation takes 12 hours, it just takes too much time to do this calculation. Okay? So what we're interested in is we want to use the supercomputer, the data from the supercomputer simulation to identify a model, okay, of this simulation code. So this is a model of a model of the simulation code. And then once we have this model, we can use this model for other simulations and save time. So for example, the simulation that I just showed you took almost 12 hours on the supercomputer. We can get a model of that simulation code and run the simulation and get the same result, practically the same result in minutes on a laptop. So that simulation could now be done on a laptop after we've gone through this identification.
Did you use OKID?
No, we didn't use OKID. We used, but the original version used EIA. So you're familiar with EIA. So one of those simulations, the model could be derived from EIA. And the difference between the EIA that you learn, well, the same EIA, but DNA that you learn, you probably deal with a small number of inputs and small number of outputs. Here we're talking about millions of output locations, because every point in space is an output location. Okay, so that's why once we have this model, we can run in minutes as opposed to hours on a supercomputer, and that's the purpose. So this is the idea again. So you have a HPC high performance computer model. You have a source signal coming in, and we have outputs coming out. We collect this input-output data and perform system identification. So if, for example, EIA can be done here, and then we have a model. Then we can, this model, we can test it by using a different source input. Okay, and this model is very fast. It can produce the output, predicted output. And so this model of this model, okay, this is a model of a model, and we can use it for different source inputs. So if you want to have a optimization routine where you have to run this many times, you just replace by this model. Okay, so that's the idea. So this problem has many features that we can take advantage of. The true dimension of the system is very large. Okay, the length of data input-output data record that is available for identification is very short. We talk about hundreds of thousands of data samples. The number of inputs is small, 1 or 2 or 3. But the number of outputs is huge. We talk about millions of output measurements, because every point in space is an output location. So we take advantage of these features to develop system ID methods that can operate with this in this extreme very fast. So okay, so I showed you the simulation already, so I'm going to skip. So that was the example of acoustic simulation. Now, this is another example of seismic simulation. So, ground vibration. Okay. So, if you have an earthquake example, you can model that as a seismic wave propagation through the earth. So now the environment is underground, okay, and we can create a model to simulate the propagation. And this is an example of a model. So this is the earth and underground here, and you go underground, and there are different layers representing different level soil, layers of soil and rocks, and these are based in this simulation. These are basements of buildings. Okay, and I want to study the acoustic, seismic signature. So, for example, if there's an impact on this surface of the earth, then you can see this response coming out. So a typical, this is input, okay, and this is output. So you will have one of those and millions of these. Okay? And I show you a simulation of that. If there's an impact on the ground, you can see again how the signal is propagated underground. Okay, so that's forward model. So that's a typical model that you normally see. Now, the next, I'm going to talk about reciprocal models and what they are. Now, there is a principle in structural dynamics. If we have a model, a forward model, okay, And the forward model